All right, this could be one of the most challenging concepts. I don't know why it is, but it's really tricky. So I highly recommend addressing your textbook. I highly recommend probably watching this a couple of times and reading through the lab handout and then paying really close attention during lab and taking advantage of every moment that we talk about osmosis to ask questions that you have, because your efforts to understand osmosis will help you tremendously throughout the semester. So make it happen. First, we're going to give a definition of osmosis, because the definition is not what you might have heard in the past. Osmosis is not the diffusion of water. Osmosis is the movement of water across a semi-permeable membrane. Now, go ahead and think this through. What is a semi-permeable membrane that we might be talking about? How about the cell membrane? Does that work for you? Of course it does, because that's absolutely what we're talking about. Water moving across a cell membrane or any semi-permeable membrane, that's osmosis. Now, why would osmosis happen? Well, okay, I think what we'll start with is this picture, because look, this actually will distinguish for us why osmosis is even necessary. Does this picture look familiar? If the answer is no, that means you did not watch this entire lecture. You punk. Go back and watch the rest of this lecture. If the answer is yes, good job. You know that this was just our example of diffusion. And in fact, look at this. My particles did diffuse. We had a high concentration over here, high concentration. This is a sign for concentration of, oh yeah, red dots. And we have a low concentration of red dots. Look, I'm going to do this, and this is a low concentration of red dots. And then what happens to my concentration of red dots after the red dots diffuse? The concentrations are equal, right? And think about that. When the concentration of red dots is equal, when the solute particles have equal concentrations on both sides, do they stop moving? We're done. Everybody halt. No, that would mean you would freeze at absolute zero if they stopped moving. They're totally still moving. And in fact, some of them, this is important, some of them are still going to move across. And that just means that someone from the other side is going to also move across, and they're like going to switch positions. So there's still total movement happening, but they're at equilibrium. Does that work for you? They're at equilibrium. That says equilibrium. Equilibrium just means that the movement in one direction is the same as the movement in the other direction, which means the net movement is zero. Does that make sense? Somebody goes this way, somebody else goes this way, and basically you didn't have any change happening. Equilibrium of particle. Equilibrium, let's call it osmotic equilibrium. I don't care. Osmotic. We have priorities. Java, schmava. It's osmotic equilibrium because do you agree that the osmolarity on both sides is the same? Yeah. So osmotic equilibrium means that our concentrations on both sides are the same. Okay. There was no osmosis that happened here. Did water move? Well, water's totally moving, but there's not a net movement of water in this situation. Why? What moved? Particles moved. Does that work? Here's the scoop. We're calling this a semi-permeable membrane. some things can get through and other things can't. In this picture right here, the red particles are considered penetrating particles. Okay, a penetrating particle can go through the cell membrane. It can go through, and in fact, these particles are penetrating because look, they all got through. Osmosis does not happen if particles in the situation are penetrating. Does that work for you? That's huge. Imagine this exact same scenario. In fact, I almost want to copy and paste it. What if the particles couldn't move? Look at this scenario over here. In fact, maybe I have another picture, and we'll just go do another one. It's not down there. It's not up there. What do I do with that thing? There it is. Now, let's say, dang it, I gave it away. We should have done it like that. Here's the scenario. These guys are now non-penetrating. What does that mean? It means they can't pass through this semi-permeable membrane. See this thing right here? Looks just like it did on the other side, right? It's a semi-permeable membrane. Some stuff can go through and some stuff can't. I'm telling you right now, these red particles, you're not getting through. So those red particles are non-penetrating. Now, look at this scenario and tell me true. If those particles can't penetrate, are we in osmotic equilibrium? Are the concentrations on both sides the same? No. This concentration, do you agree, is way higher. And it's the osmolarity. There's more particles per volume on this side than on this side. Do you agree with that? That's easy, right? You could even quantify this. We could count these up and be like, yeah, this is a 2 osmolar solution, and this is a 10 osmolar solution. This side is more concentrated. What's water going to do? Particles can't move. If the particles can move, they will. But the particles can't move. So now water is the only thing that can move if you want to reach osmotic equilibrium. Do you think that the cell does? Do you think that everything does? The goal at all times is osmotic equilibrium. And I say the goal, that says equilibrium. It's not like the cell or any, like this little YouTube isn't sitting here going, how am I going to get osmotic equilibrium? It's like, it's what automatically happens. Just like diffusion happens, particles move randomly from areas of high concentration to areas of low concentration. It just happens. You can't tell it to stop unless you put in energy and like do some active transport. Otherwise, diffusion is going to happen. Osmosis is going to happen. If water molecules can get through that semi-permeable membrane, they're going to move until osmotic equilibrium is reached. So talk to me. What do you think is going to happen with the water molecules in this scenario? Particles can't move to change the concentration, but water molecules can. Oh, that's horrid. Much nicer. Water is going to move. Water can. If water moves from this side, do you agree that we'd be decreasing the volume on this side and increasing the volume on this side? For how long? How long are we going to let water move? Until osmotic equilibrium is reached, until the concentrations, the osmolarities on both sides of my U-tube are the same. Like that. What? The water moved. Do you agree? The water moved. The water level actually increased on this side, decreased on this side, and now we have less volume for the number of particles, more volume for the number of particles, and the concentrations are equal. We are now in osmotic equilibrium. What? How cool is that? Now, that actually creates pressure. You can have, in fact, if you look at this scenario where we've reached osmotic equilibrium, think about this for a second. If I took like some big old floppy boots and I like pushed down, like stomped on that water and pushed it down, I applied pressure and squeezed the water. The particles can't go through, but I squeezed the water back over here by applying pressure. That's osmotic pressure. They're actually, like, you can do work with the fact that water is going to rush over to that side. We can expand things if water is moving. Cells can pop if water moves. This is why don't give someone an IV of fresh water. Oh, they're really dehydrated. Here, take some water into your vein. No, please no. You're going to pop all your cells because that water is going to cross the cell membrane and try to dilute the cytoplasm. And then your cell will swell and it will pop, which is a bad situation. Okay, so we can actually describe these solutions in comparison to each other using some terms that sort of might sound familiar to you, but listen to this. Let's do it like a this. I'm going to tell you that this is going to be my left side. The left side is hyperosmotic to the right side. Do you agree with that? Hyper, more. It has a higher concentration. It has a higher osmolarity when compared to the right side. The right side is hypo, and it's actually hyposmotic. But I'm totally cool saying hypoosmotic because I think that is easier for my brain to process. The right side is hyposmotic to the left side. It's hypoosmotic. It has less concentration than the left side. Left is hyperosmotic to right. Right is hypoosmotic to left. Talk to me about these two sides. Right is what? Isosmotic. Isoosmotic, they're the same. The concentrations are the same. So you can actually talk about the solutions in comparison to each other based on their osmolarities, and you can say, oh, this cell is hyperosmotic. The cytoplasm of the cell is hyperosmotic to the blood plasma. It's more concentrated in the cell's cytoplasm than it is in the blood plasma. And then you can figure out, like, what's water going to do as a result of that. The last thing I want to talk about is throwing some cells into this scene because we're going to talk about tonicity. And tonicity is not the same as osmolarity. Osmolarity is just straight up concentration. Tonicity describes what happens to the cell in the various solutions. Okay, so I'll be right back.